Okay, now it's a turn of Itak Neri, who will talk on the title of Thermodynamic Trade-off Relations Involving First Passage Times. Itak, please start.
Yes, so thank you for the introduction. Sorry for the delay, and thanks for the organizers to set up this very interesting meeting. So I will first introduce the two problems we discuss in this talk. So these are two problems that people have been studying for quite some time in non-equilibrium thermodynamics. So the first problem is about a trade-off between speed dissipation and fluctuations in the process, which is also sometimes called uncertainty, reliability, error. And this problem boils down to the following. Suppose in a three-dimensional space, I would plot reliability, speed dissipation, and the question is whether we can find a surface in the space such that below the surface, processes are non-permissible. So in this talk, we will see how to do this in a context of first passage quantities of a current. And then there's a second problem that we will discuss, which fits very nicely in the previous talk of Professor Seifert. So here we have a current that we observe, say, a current through a wire, electrons that move through a wire. And this current will have some dissipation. So measuring this dissipation is very difficult because it's an ephemeral quantity. It's energy that is transferred to a very large number of degrees of freedom, and it's lost forever. However, with stochastic thermodynamics, people have established methods to at least measure a proportion of this dissipation from the fluctuations in the current. And so in this talk, we just see how to get a proportion of the dissipation by measuring first passage properties of the current. So that's the main innovation. So let's now look at the system setup in which we consider these questions. So we'll have a current, which we denote by capital J, which in general is stochastic. So on average, we assume that this current increases over time. So it increases linear in time with a proportionality factor, which is the current rate. So since this current is stochastic, there will be fluctuations, and people have often looked at these fluctuations at a fixed time. What we will do in this talk is instead, we will look at, oh, sorry, I think, do you see the left part of the slide? Wait 1 second to move this. Yeah, sorry. So here we put two thresholds. Let's say a threshold L plus, threshold minus or minus, and we look at the first time this current exits this interval. So for different realizations, this time will be different. We denote this time with capital T because it's a random time. So not to be confused with temperature. There won't be any temperature in this talk. And yes, this time will be different for each realization of this current. So we can use this time to characterize the speed of the process. So the mean of this first passage time is the speed. And we can use this negative threshold to characterize the fluctuations in the process. We define this P minus as the fraction of trajectories that exit this interval through the negative threshold. So this negative threshold is crucial, as we will see. So we need this negative threshold to capture a significant fraction of the dissipation. And that's may have been somewhat overlooked in the literature, that this negative threshold is really important. Yes, so we also have dissipation in this process. And these quantities will be the main actors in this talk. And we will see that there exists an inequality that relates these 5 quantities. So in this setup, we haven't specified yet what's J or S dot. So we need to specify that if we want to derive a mathematical result. And for this, we use one of the main paradigms of non-equilibrium thermodynamics, which is a Markov jump process on a network. So we have a process X that jumps on the nodes of a graph at certain predefined constant rates K. So in this setup, we can define now currents. So we have first these fundamental currents, which are simply the number of times that you jump in a certain time interval from X to Y, minus the number of times that you jump backwards. And then you can define a general current in terms of these fundamental currents as a sum over these edge currents times a quantity C, which denotes the proportion of a certain quantity that is exchanged or transferred when the process jumps from X to Y. So that's a generic current. We can as well define a specific current, which is the entropy production. And for this, we use the principle of local detail balance. So we define this entropy change through the ratio to transition rates. And then we simply plug this S inside this current. So we replace C by S, and then we get what is called the stochastic entropy production. So here you can recognize the S. So there's one notable difference, which is we have added here what's often called the system entropy change. And this is because then exponential of minus S has very nice properties. For example, it is a martingale, and this will be useful when dealing with first passage properties. So this martingale will come back later in the talk. So the average of the end production is the rate of dissipation. It's the number of bits of entropy produced during the process at the rate of bits produced. So this is all well established. So these are references which discuss all of this. And this for martingales, and you can refer to the last two references. Yes, this is a setup. Let's now discuss the main result. So the main result is an inequality that relates these quantities we have discussed. So there's dissipation, there is uncertainty, which is quantified in terms of the logarithm of the probability to hit the negative threshold. There is speed, which is quantified by the mean first passage time. And then here we have the ratio of the thresholds, which is finite. And plus we have here, what is this? Well, this inequality only works in the limit where the thresholds become large. So this is a little O notation. It denotes a function that goes to 0 when the thresholds become large. So we can call this quantity here the first passage ratio. It's a quantity we can use to estimate dissipation, similar to the thermodynamic uncertainty ratio. And let me as well mention that here, so this, we could have replaced this by the current rate. That's simply equal to the current rate, but it's nicer to express everything in terms of first passage quantities. That's why we use this inequality. Yeah, right, so that's the main result. So where does this result come from? Well, it comes from this beautiful result that has been derived some time ago. So it says that if you look at the probability distribution of currents at the fixed time, then for large times, it satisfies a large deviation principle. So here we have the large deviation function. And it turns out this large deviation function is upper bounded by a parabola. And the width of the parabola is determined by the rate of dissipation. So the interpretation of this result is that if you want to have a precise, don't have a small amount of fluctuations, you have to dissipate a lot. So how do we go? So yes, let me first illustrate this on an example. So here we have an exclusion process, and you can see the large deviation function, and you see that This is the parabola that bounds fluctuations in this process. So how do we go from fixed time to random time? Well, there exists a very basic inequality which states that the splitting probability is greater or equal than the probability of a current at a fixed time. The cumulative probability, the probability the current is smaller than the negative threshold at a fixed time. But this inequality only holds at large thresholds. It holds at fixed time, but at large thresholds. And we can simply fill this bound inside here and do some elementary manipulations. And this leads to this inequality. So that's where it comes from. It comes from this parabolic bound on fluctuations of currents at fixed time. So let's compare this result with some other results in the literature. So there is this result called dissipation-time-uncertainty relation. However, if you compare these two relations, then you see that here the log p minus is missing. So there is no, in fact, no uncertainty in this relation. And as you see, so for large thresholds, so this ratio is finite for large thresholds. This ratio converges to 0 for large thresholds because the time it takes to escape a large interval diverges. So let's look at another relation, which is interesting to compare. It's called the thermodynamic uncertainty relation for first passage times. So here, the right-hand side of this relation is finite in the limit of large thresholds. So that's interesting. And so let's compare these two cases. So we have dissipation here. We have speed as well, both quantified by mean first passage time. However, this uncertainty is quantified differently. So here we use the splitting probability. Here it's quantified by the variance in the time to hit the threshold. So note that this first passage time properties here are only determined by the positive threshold because the probability to hit the negative threshold is small. So whereas here we have uncertainty characterized by events that hit the positive threshold, whereas here it's characterized by something determined by the negative threshold. So that's the difference. So which relation captures a larger fraction of the dissipation? Well, I will show you that this one captures more dissipation precisely because it's determined by properties at the negative threshold. So we can determine this in one specific case. We can really show this explicitly, and that's the case where the current is proportional to entropy production. In this case, we can derive this equality, and this is very simple to derive if we use that exponential of minus s is a martingale. Since exponential of minus s is a martingale, it satisfies this integral fluctuation relation at stopping times. And this relation, it's important that t is a first passage time with two thresholds. So here as well, the two threshold problem comes into play. Otherwise, this relation would not hold. And you will see that this relation almost immediately implies this equality. So I can simply write this out. So this is at the stopping time, we have the probability to hit a negative threshold times the exponential of L minus the value of S at the negative threshold, plus P plus exponential of minus L plus the value of S at the positive threshold is equal to 1. And now in the limit of large thresholds, I can discard this part because it converges to 0. And we find that P minus is the exponential of minus L minus. So if I now substitute this in the above equation, we see that these two cancel out. And this ratio is simply the entropy production rate if J is the current. So that's how, using the martingale, see how easy it is to derive this result. So let's now look at some examples. The first example is a random walker on a two-dimensional lattice. So this is a very simple process, simply one particle that moves forward on a two-dimensional lattice. And in this case, we have two types of currents. So there's electric current, which is how much the process advances on the x direction. In other cases, how it advances on the y direction. We can define a current in general in terms of sum of so x times the proportion of quantity exchanged when you move in the x direction plus a proportion of the quantity exchanged when we move in the y direction. And in this particular case, J is proportional to S if delta is equal to this. So let's now evaluate this first passage ratio, which appears on the right-hand side of the inequality for this simple model, 2D random walker. So you see it's smaller or equal than 1 as determined by the bound, by the inequality. But you see as well that there's one specific value where it's equal. And this turns out to be exactly the value for which the current is equal or proportional to the entropy production. You see that indeed it's the bound holds as an equality when the current is proportional to the entropy production. So as a point of reference, we can compare this with the uncertainty ratio, which people have been studying a lot in this context in literature. So this is it's basically fluctuations characterized by the variance of the current. And you see this is smaller, so you capture a smaller fraction of the dissipation, but also you see that the optimal value, the most precise current, is in general not proportional to the entropy production. That's the distinction between the two. So how can we understand that this value lies below this first passage ratio? Well, for this, what we can do is the following. We can plot these two ratios as a function of the rate of dissipation. So here at 0, we are near equilibrium. So near equilibrium, both ratios behave similarly. They capture the same amount of dissipation. However, when the rate of dissipation increases, what happens is that the first passage ratio converges to a finite value. On the other hand, you see that the thermodynamic uncertainty ratio converges to 0. So you can conclude that far from equilibrium, at least in this model, the passage ratio captures a finite fraction of dissipation, whereas the certainty ratio captures a negligible fraction. So let's now look at another problem, which is entropy production estimation for molecular motors. So this is the following problem. So suppose that we have a living cell and we label say kinesin motors with the fluorophore, and then we observe the position of these kinesin motors within the cell. So people can do this nowadays. So there exists super resolution live still imaging methods that allow cell biologists to track trajectories of molecular motors live in cells. So the question we can ask is, can we estimate the rate of dissipation of these motors from the measurements of these trajectories? So for this, we will here compare different approaches based on a synthetic model where we know the dissipation rate, and we can just compare this with estimates based on different approaches. So the model we use is as follows. It works as follows. So we say that a molecular motor consists of two motor heads. Each of these motor heads can be in three states. Either it can be bound to a nucleotide, ATP, so adenosine triphosphate, or it's bound to ADP. So this is as the version of the molecule with two phosphate groups. And the third state is a nucleotide-free state. So there are two motor heads. There's a rear motor head, there's a front motor head. And hence there's a dynamics that determines how the states of the different motor heads change as a function of time. So this is a continuous time Markov jump process describing how these motor heads change their state. So for example, so here we are in the T phi state. If now we jump to the D phi state, then this corresponds here with the rear motor head changing the ATP molecule into an ADP molecule. So this is actually a hydrolysis step. So there's one specific step in this model, which is from 2 to 5, which is not a chemical transition, but it's a mechanical transition. So if we jump from 2 to 5, what's happened is the following. So suppose we are in DT and we jump to TD, then what happens is that the two motor heads exchange their position. So this is the step corresponding with the motor moving forwards on the filament. So what we are going to assume is that this edge current is observed, and then the question is how much dissipation can be captured from this process from the measurement of this edge current only. So dissipation here is related to the efficiency of the motor, as well mentioned by Professor Seifert in the previous talk. So you have here a mechanical force opposing the dynamics of the motor, and we have the hydrolysis of ATP into ADP, which is a chemical fuel. So if this chemical fuel is completely converted into work, then the efficiency is perfect. But if there's some waste, energy waste, then the motor will have less efficiency. Dissipation here directly relates to the efficiency of the motor. All right, so now what's the problem? The problem is we want to determine this rate of dissipation, which is basically defined by this Kullback-Leibler divergence. So it's the probability to observe certain trajectory of the current divided by the probability to observe the time reverse trajectory. However, there is in general a problem here, which is that the speeds are non-Markovian, and this makes it difficult to actually determine these quantities. Therefore, we won't have access directly to this, but we'll look at other quantities. So one is this Kullback-Leibler divergence, which assumes that the current J is Markovian. Then there is the thermodynamic uncertainty ratio. And finally, we will look at the first passage ratio. So these are the three estimators of dissipation that we will use. All right, so here we have now a plot. So we plot the rate of dissipation of the motor as a function of the mechanical force, which is the force opposing the motion of the motor. And so there's one specific point here, which is denoted by this red vertical line, which is the point where the motion of the motor is stalled. To the left of this line, the motor moves forward because there's the force opposing its motion is small. Yeah. Yes, please.
Sorry, maybe I'm missing. In the last slide, you mentioned the 4 processes. So first one is there, but the other 3, is there any time derivative also involved? Like first one, I see there is a S dot there, but in this 1, 2, 3, this thing there is also.
So you mean why there's no S dot?
Yeah, there
here
are.
And here. Yes,
yeah,
yes. So so these are estimators of dissipation. So each of these quantities, they're smaller than S dot.
Okay.
And they're not really exactly calculating this, but we know that they are smaller or equal than S dot. So they capture a fraction of the total dissipation. And the advantage of these is that we can easily, we can term them more easily. Whereas here, to determine this, we would need to know what is P.
Yeah.
And so we observe J, but we don't know exactly what's P. And since J is one current in the Markov process, which we don't know, we can't observe all the degrees of freedom of this Markov process, and the statistic of J will be in general non-Markovian. So, and this complicates the evaluation of P.
Okay. Yeah.
Does that make sense?
Yes.
Yeah. Yes, and yeah, so what we will do is, so the thing is, since this is a model, we know S dot, because we know the rules of the model. And yeah, so in this case, we can actually compute S dot. And so what you see is that there is a minimum which is quite close to the stalling force, but it's not exactly zero. So this is a non-equilibrium stalled point. And yes, so we can now look at these different estimators. So this is the Kullback-Leibler divergence. So it neglects any memory in the current. Simply the Kullback-Leibler divergence, if we assume the process would be Markovian. So we see that this is the fraction of dissipation it captures about the process. Then we have here the thermodynamic uncertainty ratio. So this is the fraction of dissipation that it captures of the process. And then this is the first passage ratio. So you see what's quite nice is that here in this regime, it captures a significant fraction of the dissipation. It's almost exact. And this is the regime where the motor moves forward. So this regime, it's not perfect. And then what's also somewhat fascinating is that you see that near stalling force, nothing seems to work. So all three estimators, they capture a negligible fraction of dissipation near stalling force, which maybe makes sense because the motor is not moving forwards or backwards near the stalling force. So that's this. So this raises an interesting question because the current in the previous case was an edge current. So we can ask the question, what is the first passage ratio if J is an edge current? So we know if J is proportional to the stochastic entropy reduction, then the first passage ratio is equal to the rate of dissipation. But let's say that we know that J is proportional to an edge current. Can we say something? Can we determine actually the first passage ratio? And the answer is yes, we can. And the answer is quite remarkable. So suppose that you plot the expected value of the exponential of -8 times the edge current. So this is, and we plot this as a function of A. So a typical curve looks like this. So for A0, this will be 1, and then it will go below 1, and then it crosses 1 again at a different line. And so this value where it crosses 1 will, of course, depend on time. So it's a time-dependent quantity because J is not an end production. But there exists a specific, for long times, there exists E star, an effective affinity, which is basically where this quantity is 1, in the long time limit. And now what's remarkable is that this effective affinity measured by the marginal observer, it turns out that this is exactly the first passage ratio for the current. So the first passage ratio is this measured effective affinity through this integral relation at large times the current rate of the edge. So, and what this indicates is that it does seem that the marginal observer has some consistent thermodynamic picture with a kinetic affinity that fits with the estimated rate of dissipation. So this let me acknowledge all the collaborators whom have discussed about stochastic thermodynamics. And then we come to the summary. So we have seen this trade-off relation. So it's a trade-off relation that involves all sort of first passage quantities. So so this gives us a certain quantity, this first passage ratio, that allows us to estimate the rate of dissipation. So we know that if J is proportional to the current, then this is an equality. We have as well seen if J is proportional to an edge current, then we can as well determine this first passage ratio, and it's consistent with thermodynamics of a marginal observer. And yeah, we also, a nice thing about this relation is that P minus is a splitting probability, and we can use martingale methods to determine splitting probabilities. So for many scenarios, we can actually exactly determine this first passage ratio. Yeah, and if there's, so thank you for your attention, and if there's any questions, I would be very pleased to answer them.
Thank you very much, Itzhak. Yes, please start by Udo.
Okay, yeah, thank you, Itzhak. Very nice talk. So you have pointed out that your estimator typically beats the uncertainty relation and other ones. Now, your estimator also has additional parameters, right? I guess it depends on what you choose as L minus.
Yes, absolutely. So this, for time issues, I haven't gone into that, but indeed, so the first passage ratio, so all the results I presented are only true in the limit of large thresholds and infinite number of realizations of the process. So you can ask the question, what happens at finite thresholds and for finite number of realizations? And then it still works very well, because the nice thing is that even if you don't observe any event that has a negative threshold, you still get information about dissipation. Like even zero events hitting negative threshold gives you some information about dissipation. But the number of realizations that you need to guess correctly the value of dissipation, it does increase exponentially as a function of the number of dissipation, and that's because it gets increasingly unlikely to see events at a negative threshold. So you saturate. So the actual value increases as a function of the number of realizations until it saturates at the point where you start seeing events that hit a negative threshold. So this is all is explained in the Journal Physics A paper.
Okay, so yeah, thank you. Okay.
So,
Hello.
Arnab, please.
Hey, hi, Isaac. Thanks for the nice talk. So I was just wondering, sort of a general question. So I don't really follow the log term essentially, which is appearing in your inequality, because you are just, as you have mentioned, if I just also consider the Horowitz paper, the first paper with one threshold.
Sorry, I couldn't hear it well. Could you
okay,
repeat
so,
your question?
Okay, there is some noise issues over here. So if you could just look at the chat box, maybe.
Oh yeah, I will look at the chat. But it's related to the, I don't know why the log appears in the mean inequality, because sort of going from one boundary to two. And actually one would think of conditional perspective replacing the global perspective. Yes, so the log term, it has to be there because this can be understood from the fact that P minus, decreases exponentially in minus L minus. So P minus has for large thresholds a form of exponential minus L minus. So this is the correct scaling with the L minus. And yes, so here, so here in the equality case, it's really, this is the most simple case to see where it appears. So you see that you have here P minus exponential L minus. So if L plus goes to 0, and you have P minus exponential L minus is 1. So from this, you find that P minus is equal to exponential minus L minus. So here in the equality is the most easy to see. And the inequality, yes, you have to see, yes, here as well, there's an exponential, right? So probably that leads to the log here. But I have to, for inequality, I should look a bit more carefully. But I guess it's because the probability has this large deviation form that the log appears. I don't know if that answers your question.
Thanks.
Yeah.
Sure.
The Sourabh, please, pose your question.
Hello, Isaac. I could understand this problem by visualizing a lattice with say ensemble of non-interacting random walkers. So I was just wondering whether a general relation exists when there are multiple interacting random walkers. Just for estimation of dissipation. Suppose self-excluding particles.
Yes, so these relations, they hold generally for stationary Markov jump processes. So if you include interacting particles, the relation should still be valid. That doesn't change because everything, so the derivation relies mainly on this result, which holds for non-stationary Markov jump processes. Stationary Markov jump processes. So interactions shouldn't change much, but indeed here, this curve will of course change. This is a specific curve for this model, but it will remain, so it will remain below 1. So this inequality remains valid. And the fact that it should be an equality for J equals to S should remain valid as well. So that's right.
Thank you.
Okay. Edgar, please.
Yes, a very short question. So the bound based on P minus L plus L minus, it looks very similar to our 2015 result. So what is the main difference? Because I remember rewrite it in a similar way, no? That result.
Yes, absolutely. No, it is very related. But yes, if you look, it seems that, so I went back often to that paper where I think we put one equation there, which is inequality, which is similar here. But I think, so there it seems that we look at symmetric thresholds, and we have, yes, we have this, if you look at asymmetric thresholds, what it appears there is P dagger, the probability in the time reverse dynamics, and not in the forward dynamics.
I see. So this is a generalization.
It's closely related. It's definitely closely related.
So this is a generalization to arbitrary thresholds, also asymmetric.
To asymmetric thresholds, and it's a different. I think in that paper we relate this to sequential hypothesis testing. So the nice thing was to as well understand that it's related to this bound on the large deviation functions, which somehow connect this to uncertainty relations. And yeah, as well, in the paper as well clarified some of the because there in that paper we were not really careful saying it holds for large thresholds. We kind of understood the connection. We kind of understood it's interesting, but exactly conditions weren't so clear when this inequality holds. But definitely it's closely related to that. So that's why I'll put reference.
Okay, thank you.
Okay, thank you again, Itzhak, and thank you for the audience.